Hello everyone and welcome back. My name is Mr. Cobalt and this is the third segment of going through practice problems involving Lewis dot structures. And so the next one I'm going to go over is phosphoric acid. This is a particular special one because you'll notice that phosphoric acid begins with hydrogen. And as I've said before, hydrogen is not going to be a central atom. So watch out for that. But like in all these problems that we've done, and we will do, the first step is always to figure out what the total number of valence electrons in your molecule is. So we have hydrogen. So hydrogen is in group 1, so therefore it has one valence electron, but we have 3 of them. So that's going to be 3 valence electrons. And then we have phosphorus. Phosphorus is in group 5, so it has 5 valence electrons. So write the +5. And then we have 4 oxygens. Each oxygen has its own valence electrons. Oxygen is group 6, so it has 6 valence electrons. So 4 times 6. 4 times 6 is 24. And so now there's no charge, so we don't need to worry about adding or subtracting due to charge. So this is going to be 24 plus 8 gives us what? 32. So we have 32 valence electrons. Okay, so that's a lot of valence electrons to use. Okay, so the first thing, coming back to the skeletal structure. So since a lot of times the first atom in the formula is going to be the central atom, but in this case it's hydrogen. Hydrogen is never going to be a central atom because hydrogen can only bond once because it only has one valence electron to pair up with another atom. So that's not going to be the central atom. So if you start with hydrogen, skip that one, go to the next one, and usually it's the next one. So phosphorus is the less electronegative atom compared to oxygen. Oxygen is more electronegative. Phosphorus has more unpaired electrons in the Lewis dot structure. So phosphorus is definitely going to be our central atom. So everything is going to be bonded to phosphorus except the hydrogens. So whenever you have an acid that begins with hydrogens, the hydrogens that are beginning the acid are bonded to the oxygens. So these 3 hydrogens are going to be bonded to an oxygen. So the oxygens are going to be bonded to phosphorus. So let's follow our steps here. So we're given phosphorus is our central atom. We have 4 oxygens. So the 4 oxygens are going to be bonded to the phosphorus. And our 3 hydrogens, 1 hydrogen is going to be bonded to each 3 of the oxygens. So I'll do these 3 since I gave myself some space, and there's no space up here. Okay. So this is my skeletal structure. So the acidic hydrogens are bonded to the oxygens, and this oxygen doesn't have anything bonded to it. Okay, so we've got our skeletal structure. So now we have to subtract out the electrons that we used in the bonds. So there's 2 electrons per bond. So how many bonds do we have? We have 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14, so we're going to subtract out 14 electrons, and that gives us 14, 32 minus 14 is going to be 18 electrons left over. Okay, so now I have 18 electrons. So the next step after you have your skeletal structure is you give lone pairs to the outer atoms until they have an octet. So the hydrogens are good with their duets because they're sharing 2 electrons with the oxygen. So these hydrogens are fine. I don't need to give lone pairs. But then the oxygens here do not have octets. So these oxygens have 2 bonds. So they need, that's 4 electrons. So they need 4 more. So they need 2 lone pairs each. And this oxygen only has 1 bond, so it needs 3 lone pairs. So let's go ahead and give it to them. So 1 lone pair for this oxygen, 1 lone pair for this oxygen, and 1 lone pair for this oxygen. And then we'll give 3 lone pairs to this oxygen. Okay, so now we have our lone pairs. We count up the lone pairs and we have to subtract that from the 18 electrons we have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 is 18. So I'm going to subtract out the 18 and I'm left with 0 electrons left over. So at this point I have no more electrons. I can't give electrons to my molecule here. So now I'm going to double check to make sure everyone is happy with an octet or a duet. So as I said before, my electrons are happy with a duet. This oxygen has 2 bonds and 2 lone pairs. So it fits the bonding pattern. So it has 8 valence. It has 8 valence electrons. It's got its octet. So 2 bonds, 2 lone pairs. 2 bonds, 2 lone pairs. 2 bonds, 2 lone pairs. So those 3 fit the bonding pattern. Here we have 1 bond and 3 lone pairs. So that's going to be an octet. So that's got 8. And then phosphorus has 4 bonds. So 4 times 2 is 8. So everyone's happy. So this is a legitimate Lewis dot structure. Now some of you might be thinking, wait a minute, you might have learned from other classes or from before when you did chemistry 108 or whatever chemistry class you took, that this isn't quite right. That's true. This is a good Lewis dot structure, but the question then is it a best Lewis dot structure? Is it the best representation of what the molecule is? We're going to get to that later, but what I want you to see is that this is a legitimate Lewis dot structure. May not be the best one, may not be the most important Lewis dot structure for this element. We're going to deal with resonance structures later, and so so this is legitimate for now, right? So everyone's got an octet, everyone's got a duet, everyone's happy. So this would be a legitimate Lewis dot structure. So we'll leave it there. I'll come back to this in another video and talk about when we talk about formal charge. Okay. And so just to be more specific, so we might change this so that this has a double bond, right, with 2 lone pairs. So I can move one of these and create a double bond, and then that would give 2 lone pairs and 2 bonds fitting the bonding pattern of oxygen. But then you'll notice if I have a double bond here, then I'll have 1, 2, 3, 4, 5 bonds around phosphorus, which means it would be more than 8, which is 10. And that seems strange because we've been talking about rule of 8. But then again, some atoms can have what is called an expanded octet. Again, that'll be for another video. Okay, so this is a legitimate Lewis dot structure. So we'll go on to the next one. Okay, so phosphoric acid. What about this one here? So we have selenium, oxygen, and fluorine. So of these 3, selenium is going to be the less electronegative atom. It's the one written first. And so these guys, this oxygen and 2 fluorines are going to be bonded to selenium. So first thing we need to do is figure out what the total number of valence electrons. So selenium, I believe, is in group 4. No, it's in group 6 with oxygen. So selenium is in group 6, so that means it has 6 valence electrons. Oxygen is in group 6, so it has 6 valence electrons. And fluorine is in group 7, so it has 7 valence electrons, and we have 2, so that's 14. So plus 14 for the fluorine. There's no charge, so we don't have to worry about adding or subtracting. So we add these together, and you get 26 electrons. So then, now we're going to do this, the skeletal structure. So like I said, selenium's written first. Even though selenium and oxygen both have 6 valence electrons, therefore they have 2 unpaired electrons, so they're the same. But selenium is definitely less electronegative than oxygen, and hence the reason it's written first. Usually the less electronegative atom is written first. Okay, so selenium is going to be our central atom. We're going to have 2 oxygens. Oops, that's 1 oxygen. We'll have 1 oxygen, and we'll have 2 fluorines bonded to the selenium. So this is our skeletal structure, just single bonds between everything. So we used 3 bonds for our skeletal structure. So that means 2 electrons each. So we need to subtract 6 electrons from our total. So minus 6 electrons equals 20 electrons left over. Second step is we now take, third step is now we take electrons from here and we put lone pairs on the outer atoms first to give them an octet. So fluorine has 1 bond, so it needs 3 lone pairs here. Again, this one has 1 bond, so it needs 3 lone pairs. And oxygen has 1 bond, so it needs 3 lone pairs. So 3 each. That's 3, 6, 9. So 9 total. 9 times 2 is 18. And so we subtract 18 and we have 2 electrons left over. Okay, so the next step is we apply lone pairs to the central atom to make sure the central atom has an octet. So the central atom, selenium, has 3 bonds, so it needs it needs an extra lone pair. It needs a lone pair to get an octet. So we're going to put a lone pair here, and so subtract the 2 electrons, and we have 0 electrons left over. So now we double check to make sure our atoms all have an octet or duet. There's no hydrogen here, so everyone should have an octet. So fluorine has 3 lone pairs, 1 bond, that's 8. This fluorine, same thing, 8. And this one, again, same thing, 8 electrons. And the selenium has 3 bonds plus a lone pair, so that's going to be 8 as well. So everyone's happy with an 8, and this is a legitimate Lewis dot structure. Again, might not be the best or most important Lewis dot structure. We'll get to that in a moment. We'll get to that later when we talk about how to figure out if there's multiple Lewis dot structures because of resonance and formal charge. We can figure out which one's the best. Okay, so in the next video I will continue with the last 3. I'll go over those fairly quickly, and then we'll move on. And in future videos, I'll put out, we'll talk about resonance, we'll talk about formal charges, we'll talk about how to figure out which Lewis dot structure is the most important using formal charges. And so I'll go over that. Thanks for joining me. If you like this video, like and subscribe to the channel, hit the notification bell, and make a comment in the comment section. Thanks for joining me, and I'll see you next time.